Predicting media memorability task in MediaEval 2020 has some challenging aspects compared to previous years. We propose direction to overcome some of the challenge and present our initial results. The short video used in previous year challenge were extracted from raw professional footage that is used, for example, in creating film and commercial. The majority of videos therefore contain only one scene and are mostly static. Conversely, the data for this year challenge contain multiple scene change in one video and thus are more dynamic and with more complex movement and activity, as can be seen from this graph that shows the difference in the mean optical flow distribution from the two datasets. In addition to the features extracted from frame-based deep neural network, human-centric features such as emotion or aesthetic or text caption provided by human annotators, this year dataset provides an unexplored challenge for methods that can capture semantic features from highly dynamic video. Another difficulty in this year challenge is the dataset size. Compared to previous year, this year training data of 590 video is an order of magnitude smaller compared to 8,000 video for training and validation of last year challenge. On the challenge to this year dataset made the task considerably more challenging, as the video are more dynamic and thus making the extraction of high-level semantic features more difficult, which is further compounded by the limited size of the dataset. To quickly establish a spatial temporal baseline, we use the extracted feature from the video-based C3D model instead of other frame-based methods. C3D architecture composes of small 3D convolutional kernel, expanding it on height, width, and time dimension. Trained on a generic action recognition dataset, each video passed through C3D returns a 4096 dimension vector that extracts high-level features from a video segment. On top of that, we implement a multi-layer perceptron module with two hidden layers of 512 units, followed by a ReLU activation. We also use batch norm to help with optimization, dropout to mitigate the overfitting problem, and L1 loss instead of L2 to avoid any issues with outlier in the score. For large-scale memorability pre-training, we use the Memento 10K dataset containing 10,000 high dynamic video that is more similar to this year datasets instead of pre-training on last year data, even though they have the same number of videos. We pre-trained the SemNet model accompanying the release of the Memento 10K dataset, which contains 4 separate subnetworks to process different input streams: image, optical flow, video stream, and the semantic caption. After pre-training SemNet on Memento 10K data, we only retain the video stream subnetwork to fine-tune on the MediaEval dataset and discard on other components. Due to technical error and time constraint, we only submit our baseline results in this year challenge. Even with the simplest possible regression model based on C3D spatial temporal feature, the results are not very far from the mean. This supports our hypothesis that spatial temporal representation is important for this year dataset, and the performance can be increased with other complementary high-level features in future works. On the other hand, compared to the state-of-the-art result in last year challenge, the mean of the Spearman rank correlation for on-run this year is in order of magnitude lower. This highlights the importance of large-scale pre-training and transfer learning technique and methods that can extract high-level features from dynamic video effectively. We believe the direction of our solution, given the challenge we identified, not only show promise but also indicate the importance of spatial temporal model to capture high-level semantic of video for memorability prediction.